Hey folks, welcome back to EarthSky. I am Dave Adalian. Today I have a real treat for you, something exclusive that you're not going to find anywhere else, and that is an insider's look at the world's largest, most powerful, and most resolved, if you will, digital camera. It's the heart of the Vera Rubin telescope, and it is going to help us to relearn the cosmos. My guest is Steve Bellavia, and I'll let myself introduce him right now. Let's take a look at this. Enjoy. It's about a half an hour long, so sit tight and get your. Hey, folks, welcome back to EarthSky. I'm Dave Adalian, and today my guest is Steve Bellavia. He is an astronomer's astronomer, a man who works on telescopes at every level, from the ones you'd find out in the field at any star party to the telescope at the Vera Rubin Observatory. Steve led the team that designed and built the world's largest digital camera and the system that keeps it at a frosty minus 100 degrees Celsius. Today, he's here to tell us about that project. Welcome to the show, Steve. Welcome.
Hey, thank you. Thanks for having me.
Hey, I'm so pleased you could be here. Why don't we take a quick look at a video that I grabbed. This will show us basically what this thing can do, what the Vera Rubin can do. Oh, wow, that is something special. So the camera your team built at the Brookhaven National Lab, it's performing the Legacy Survey of Space and Time, the LSST, which is the primary mission over at the Rubin Observatory. Can you tell us, what is the LSST? What's it looking for, and where is it looking? And while you tell us that, why don't we look at what it can do?
Okay, well, thanks. Originally, this started with the name of the Dark Matter Telescope. This telescope was originally, conceived and being built, before anything actually got built, just on paper and conceptually, to help with dark matter studies. And the thing with dark matter studies is this is more cosmological than it is astronomical, for those that don't know the difference. But cosmology is like big picture astronomy. Like, imagine you want to look at a city and you look at all the buildings and their size and shape and how far apart they are. Whereas in astronomy, you might want to see how that building is built. Did they use bricks? Did they use mortar? So cosmology is big picture astronomy. You need lots of data of lots of galaxies and supernovae and quasars. So it was originally built as a cosmology telescope, but the difference being that it can be an astronomy telescope too. It's not just a wide field telescope. It's a high resolution telescope. So it's both, and it's the first time it's ever been both. And nothing has ever been done like this before. So the inventor of this idea, and there you go, there it is, built in the top of the Cerro Pachon Ridge in Chile at 7,500 feet altitude. But the person that invented this is Tony Tyson. Tony Tyson was frustrated. There were scientists waiting years to use a telescope, years. So there's, by the way, there's only 4 telescopes on Earth that are of this size class or larger. So when you need to do this kind of astronomy, you have to get together with a group of people. You have to write a proposal with this group of people and then submit it to a non-biased committee that will decide if you get to have 1 week on one of these 4 or 5, 8.4 or larger meter class telescopes. And then you get your week on it. And then you have to write another proposal to get another week a couple of years from now. And this is ridiculous. I mean, Tony Tyson's like, this is ridiculous. There's too many questions to be answered in astronomy and cosmology and not enough telescopes to do it. And this is the birth of LSST, which later became named Vera Rubin. And the reason it got named Vera Rubin is she is sort of the mother of dark matter. She and Kent Ford at the Carnegie Institute DC were studying punch cards. Yes, punch cards. People may not remember them. that had spectroscopic data on it of Andromeda Galaxy. And they thought something was wrong because it seemed to them like the outer arms, the outer portions of Andromeda Galaxy were rotating, because that's what spectroscopic data lets you do. It lets you see velocities. That the outer portion of the galaxy was rotating at the same speed as the inside, which violates all of Newton's and Kepler's laws that we've, adhered to for, 400 years. That things that are on the outside of a rotating system should be going slower. Pluto, whether it's a planet or not, goes slower than Mercury, and by a lot, but not in these galaxies. And so even if and it's a matter of mass and distances. It's a simple equation, Kepler and Newton's laws. And what they discovered was that you'd need about 10 times more mass than what the estimate of the mass of the stars that you could see. In other words, the luminous matter. So, we've always believed that stars, like our solar system, that the sun's mass is 99 and then a bunch more nines % of the mass of the whole solar system. And even Jupiter doesn't even fit into one of those first decimal places. And we assume that in galaxies, if you know all the stars, you know the mass. But we're off by a factor of 10. In fact, let me see if I can find this quote from Vera Rubin herself. She says, in a spiral galaxy, the ratio of dark to light matter is about a factor of 10. That's probably a good number for the ratio of our ignorance to knowledge. We're out of kindergarten, but only in about 3rd grade. So she realizes that all of a sudden she's discovered we're missing a lot of stuff. And this is the original purpose of Vera Rubin.
Okay. And so it was designed as an astronomical and a cosmological instrument so that you could get either a good astronomical view like this one, or you could get the cosmological view. And these are the same, this is the same image, I believe.
Right. This is the same single 15-second image. And that's the other amazing thing. These images happen in 15 seconds. You get a high resolution, deep, low magnitude resolution image in 15 seconds.
Why don't we take a look at the slides that you sent?
Okay.
What are we looking at here, Steve? This is a comparison of telescopes, of their resolution and of their
field of view.
Field of view. Thank you. So why don't you run us through this?
Okay. So we've got the Keck Observatory, which isn't a fair. Keck was designed as a single-purpose astronomy telescope. It has a very large mirror, so it has good resolution, and it has a good camera. LSST with the same resolution as Keck. So in other words, the arc seconds per pixel on the camera, it just has a lot more pixels. It just expands that resolution to a much larger field of view, several hundred of Keck's field of view. So there's a parameter called étendue, which is a figure of merit for a telescope. And it's essentially the field of view multiplied by its aperture or its resolution capability. So LSST has several hundred factors of étendue over Keck. And then in between, I show the Sloan Digital Sky Survey telescope, because Sloan was designed as a survey telescope. So it's a more fair comparison. But even then, LSST is several factors, almost a factor of 10 more than the Sloan Sky Survey. So LSST can cover lots of ground. So this is more of a joke, but this is my telescope on the right and Vera Rubin on the left. And the reason I show this is because if you look at a single image of Vera Rubin on your computer or on your phone, you're not going to appreciate it, because there's no way that your phone or your single computer screen can show the difference in the resolution of these two images. So on the right, my image, and then I have the Trifid because I couldn't fit it on my telescope, though Vera Rubin did. Trifid and Lagoon. Trifid's on the left, Lagoon's on the right. I kind of like my image better. Maybe that's because you don't want to call your own children ugly. But the difference is when you start zooming in. Now, the interesting thing is the picture on the left is actually not full resolution at all. It's just, it's sort of made for computer resolution. It's off by another factor of 8.4. The actual image is actually 52,000 by 84,000 pixels, and I've only got 6,000 by 10,000 of them, because that's all Vera Rubin is releasing right now. They actually did send me a full resolution image, and I couldn't open it. But if we keep zooming in,
it would take a 40 by 40 foot
monitor. You need a 40 foot by 40 foot monitor to show the full resolution. So rather than get a 40 foot by 40 foot monitor, let's just keep zooming in. So then so here first I just get the field of view is the same. This is actually identical. The images are registered and plate solved together, so it's identical fields of view. So that's at the same now field of view scale. In other words, it's the same exact part of the sky. If you go to the next one.
What aperture are you using on your personal scope?
So Vera Rubin is 8.4 meters. I'm 0.09 meters. It's a 90 millimeter telescope versus an 8.4 meter telescope. And you'll see why that matters. So then I fix up Vera Rubin a little bit. I'm like, I don't like their rendition. I did, and now it's starting to look better. Now maybe I start to like Vera Rubin a little better than mine. And then we just start zooming in. So we'll take that region and we'll zoom in. And they're still comparable, right? I still have structure and detail, but the Vera Rubin might have a little more detail at this zoom scale. Now, you got to realize this zoom scale is still a factor of almost 10 from the actual full resolution image, but you'll see it doesn't matter how good Vera Rubin is, just blows it away. So then we zoom in again. Let's zoom into the next level. All right, I'm starting to see maybe Vera Rubin has a little more finer structure than my 0.09 meter telescope. And then we'll fix their image up one more time. And there you can see the difference. I mean, this is still a factor of 10 off, but the Vera Rubin image, it's almost like this is where it started from. Like this image alone, even at a thumbnail, 222 by 320, is full of all kinds of information and detail that mine doesn't have. So this is the point of Vera Rubin. You're not going to look at a full Vera Rubin image on your computer. You can't. You can only look at pieces of it if you want to appreciate the full resolution. Now, for cosmology, we don't need that kind of resolution. But, so this is why it's both an astronomy and cosmology telescope.
Okay. Yeah, here is just the camera. This thing is the size of a car?
No,
a bus, huh?
Yeah.
Okay. All right. So I assume there were obstacles that your team had to overcome to build the largest digital camera ever. Was there any particular challenge that you're proud of that the team was able to solve, to overcome?
That's a funny question because my answer is there was nothing but obstacles. Nothing. This was day to day. We need to do a miracle to get to the next step. I mean, and I'm not kidding. This was 10 years. Well, the first 2 years, 4 of us at Brookhaven Lab were volunteers for 2 years. And we did this at lunchtime and started, soliciting vendors for censored microchips and for electronics and, so it started off that way. And then eventually we got funding and we were off and running, but everything was a challenge. The sensors themselves were challenging. The thermal, which was my part of my main contribution to Vera Rubin, was the thermodynamics and the thermal management of the camera. The sensors have to be at minus 100 degrees C to reduce electronic noise. And then the electronics would have been nice for them to be at minus 100 degrees C, but they don't make electronics that run that cold. So we had to keep the electronics at minus 40 C, which is their lowest operating temperatures. And the electronics are a millimeter away from the minus 100 degrees C. And this is that's a tough trick to have two things 60 degrees apart, almost touching each other. So you showing a nice exploded view. It's an amazing system. The camera is not just sensors. To get to the minus 100 degrees C, we have a full cryostat, meaning that we have a facility that pumps fluids around, cryogenic-like fluids, to keep it cold. There's a utility trunk for pumps and expanders, compressors, and then there's tons of electronics. There's 3.2 gigabytes of data gigapixels of data that has to come out of one end, and then it's sealed. It's inside a vacuum. The whole thing's in a vacuum. That's how we keep it clean. The front lens, the last lens of the telescope, is the seal for the camera. And that lens has to be figured in such a way that when you pull a vacuum on it, the final shape is correct. This is another magic act that has to happen. We have to configure a lens and then distort it by several millimeters of vacuum and have it reach its correct optical figure. It's insanity. Like every step of the way, the question was, how are we going to do this? and how are we going to do it precisely? And that's the other thing, so you were asking about technical challenges. On the sensor itself, we have to have, within a micron worth of flatness, meaning we can't have any peaks of valley on the sensor that are more than a micron. Sensor to sensor, we can't have more than like 5 microns. And then there's 189 of these. Of the 189 sensors that form the image plane, we can't have more than 10 micron deviation. Now, we're talking fractions of the thickness of a human hair from one end to another of a thing that's about the size of a coffee table, while it's being cooled down to minus 100 degrees C, while it's moving around in the telescope. Like I said, it was every step of the way was a miracle. I mean, I'm not exaggerating. It was, we lost sleep, we worked long hours and long days, and when we finally tested and reached the specifications, and that's, by the way, that was the beauty of Vera Rubin. It was tremendous systems engineering, and that's where I have to give SLAC, Stanford Linear Accelerator Laboratory, credit, is they were the system engineers. They told us what specs we had to meet. And this wasn't loosey-goosey stuff. These were verified through tests and multiple tests of everything, of quantum efficiency, of charge transfer efficiency, of everything, you know, dead pixels, hot pixels. We had to meet a 1,000-page bound book of specifications before we could deliver the unit. And like I said, every step of the way was okay. How are we gonna do this? This is really hard and has never been done before. You know, most of what we did was new. Like, for example, buying sensors that touch each other edge to edge. You know, these sensors, you can't have gaps between them because then galaxies and stars fall on them. So we're practically touching, but not. Maintaining that was almost an impossibility. You know, and then to ship it across the country and have it survive, and then to ship it from California to Chile and have it survive. These were all, like, people, you know, I kid around, but saying, you know, the shipping of the sensor was almost as big an engineering hurdle as building the sensors. You know, you have to get it there. It's a precise instrument. And that's why, by the way, that's why I got picked to work on this project. Is for 32 years, I've been working at Brookhaven Lab, and my main function as a mechanical engineer was building detectors for particle accelerators, where we have gigabytes or gigapixels worth of data collection. And in the case of particle accelerators, it's muons and pions and quarks and gluons. In the sensors case, it's photons, but as far as a detector person, it doesn't matter. So I was familiar with building these precise mega data worth of data coming through on a precise instrument. And in this case, the particles were photons. Okay. So this was the challenge. Everything was a challenge. Thermal, structural.
There was no easy part to this. This was all.
The only easy part was that. The only easy part was that was working with such great people that was also like me, is into astronomy as little kids and got to grow up and do it. You know? Yeah. Well, the results appear to be worth it. We're looking at Trifid and the Lagoon. Lagoon's the bigger one. Just amazing. So let's get back to the survey itself, to the LSST. Why is the survey important, and what do we hope it's going to show us? What's it going to reveal as we go along here? Okay, that's an excellent question. There's actually 5 science missions. We already talked about dark matter. That's number 1. Number 2 is dark energy. Related somewhat to dark matter, but not exactly the same. Dark energy, you're really measuring mostly spectral shift, velocities, things like that. And by the way, Vera Rubin is mostly a visual telescope, but it does go pretty far into the near infrared. It goes up to 1,100 nanometers or 1.1 microns. And in the other direction, it goes to 300 nanometers or near UV. And those filters will help with identifying redshifts of objects, which brings me to the third science mission, which is supernovae. So dark matter, dark energy is cosmology. Supernovae are on the cusp of astronomy cosmology. The supernovae themselves, how they evolve, how they explode, the first few minutes, hours, days of their light curve, that's astronomy. But how far they're redshifted, that's cosmology. So supernovae is the third science mission that so here's the only problem with LSST, and it's not really a problem, it's its mission, is it doesn't stop. When it finds like a new star that exploded, it can't stop and look at it. It's got to keep going every 15 seconds. So it's really 30 seconds. It takes 2 15-second exposures and moves to the next part of the sky. And it does this all night long, every day for 10 years. So it can't stop. All it can do is record that data and send out like what would be the equivalent today of a telegram to other observatories to say, oh, by the way, we just discovered a supernova. Go look at it. We can't. We're moving. We're busy. So the astronomy part doesn't get done by us. It gets signaled by us. We're the messenger of that a new supernova has been discovered. That's the third science mission. The fourth science mission is mapping our own galaxy. Now that may sound like, well, what's the big deal? But as you know, I teach at night at a community college, and I tell my students about mapping the galaxy. Imagine you're inside your living room, and I say, tell me what the shape of your roof is, but you're not allowed to go outside. We're inside the galaxy. it's very hard to map something you're on the inside of. It's so much easier from an outside view, but we can't get there. So we're going to try to map the galaxy way more accurate. The Gaia satellite did a great job, so not discrediting any other maps that have been created. But Vera Rubin's going to, probably several factors, if not 1,000 times more accurate for mapping the shape and size and density of our galaxies. That's the fourth science mission. And number five was a late add-on, but it might be what got us funding, was near-Earth object detection. What Earth objects is a big one, because there's really no better telescope on Earth. I mean, there are telescopes on Earth doing this. There's Atlas and there's Catalina, and the list goes on and on, of telescopes trying to, at least maybe not save the Earth, but at least warn the Earth that something's coming. So Vera Rubin now is also a near-Earth object observatory, and all without changing anything in the design of the telescope. It's already designed to be fast, high resolution, low magnitude gathering, like down to magnitude 22 for a single image and 26 after 10 years of stacking or integration. So it's already got it in it. So there was no reason not to add on this fifth science goal.
I assume then that because the data collection is ongoing, isn't going to stop for 10 years, there might be other projects that you could dig out of that data set, right? I mean,
the digging will go for many years after Vera Rubin. I mean, Vera Rubin's designed for 10 years. I hope it goes longer. I hope they, extend it to 20. But even if it goes 10 years, it's about 20 terabytes a night of data. That's like 40 of my laptops, fills up every single night. There's going to be enough data for scientists, for PhD students, for kindergarten students. I mean, there's no reason a teacher couldn't track an asteroid that was just discovered throughout the year. Let's keep an eye on it. We're going to get a picture every night of this asteroid boogieing along in our own solar system. And so, by the way, so we're talking about near-Earth objects and asteroids. Right. In a 10-hour engineering run, 10 hours, Vera Rubin discovered 2,000 new asteroids.
What? That's insane.
Crazy, right? It is insane. Right? 10 hours.
10 hours.
Vera Rubin got 2,000 new asteroids in our asteroid belt. And so this is also, if you're sitting in your living room and want to use the Vera Rubin data, you can discover a comet. And a comet's the best thing to discover. Do you know why?
No, why?
It's the only astronomical object that gets to have your name on it. Everything else is numbers and letters. So a comet, you could be Rubin/Bellavia or Rubin Adalian, or whoever discovers that comet sitting in their living room sifting through Vera Rubin data gets their name on it. So, but so near-Earth objects, comets, asteroids, and anything else in our solar system.
So you guys, you didn't just build the camera, you built the system. You specifically worked on it, and you told us how delicate and precise the tolerances are. So are you done? You finished building that cooling system and the camera, and your hands off?
So we built 21 modules that have 9 sensors each, and we delivered them to SLAC, and they installed them, and that became the camera. Each module is 9 sensors, and each sensor is 16 megapixels. And this is interesting too. A single module, that we call it a raft or a raft tower array in RTA, or raft tower module RTM. A single raft is likely better than any camera in any telescope on Earth, and we have 21 of them next to each other.
Wow!
So we got a lot of phone calls of observatories saying, "Could you build one extra raft for us?" And we couldn't. We weren't allowed. We're the Department of Energy, National Science Foundation. We're not allowed to build for other people, but boy, they wanted one. So after delivering the 21 rafts, we were done, but we're kind of on call. So that's my answer. We're done, but we're on call. We're still the experts. We still understand it better than anybody else. So if they're having a problem with something, we're called back onto duty, but they will never come out. The telescope is not serviceable. Like if something breaks in the camera, you don't take the telescope apart. You're done. So they were designed for, a more than 20-year life. So we're hoping we never have to, get into that situation. But so far, knock on wood, everything is working. That's what the engineering run was for, to prove that everything's working. All 189 sensors are performing to specification, and they're very tough specifications. Like I said, this is the best camera on Earth right now. I don't know if there'll ever be another one like it. And it's interesting because we had 2 sensor manufacturers competing for this. E2V in Europe and STL, which is United States and Canada. And it was really going to be a sad day when we had to pick one and tell the other one no, because they put in a lot of free stuff to win this contract. And it had a very serendipitous ending. We were running behind on the schedule to produce the 189 sensors and had to pick both. So they both won. Both sensor manufacturers won. It was about 50% from each because we just couldn't get sensors delivered fast enough. We were like, we have to, get a sensor, put it into the array, finish a module, and put it aside until we're ready to ship it out. And we had to do this over and over again. 189 sensors at one a week, going into the module, do the math. That's 189 weeks. That's 3 years, It's more than 3 years. And we didn't have 3 years. So it probably took a good full week, and I'm talking 12 hours a day, maybe more, 7 days a week, to build the tower module, to assemble it once we were done with everything else, all the testing and thermal management and everything else. And it includes electronic circuit boards and, cooling straps, it goes on and on to build one of these things. And, if they said, even with the 21 modules, even that was half a year. It took us, once we were done, 6 months just to build them. Once we were done with all the design and engineering and reviews and testing reports, so it's a big project. I said it took many years. It's interesting because I was an amateur astronomer since I was 10 years old. And it was only when I was into my late 50s that I actually got to work on a project like this. And it was really hard, be careful what you wish for.
Yeah, no kidding. Hey, let's talk about that for a second. All of this work on the Vera's camera took place at the Brookhaven National Laboratory in New York. And you were the principal engineer for all of that and the cooling system and et cetera. At the other end of the scale, though, you're also an assistant adjunct astronomy professor at your local community college. You mentioned that. And you do community outreach for the Custer Observatory on Long Island. Mm-hmm. Why, Steve, are you so interested in astronomy?
That's a good question. I think it was a childhood thing, like around, I think around 10 years old, children go one in two directions. They either love space or dinosaurs. I don't know. It seems to be the two directions. So you're either going to be a biologist or an astronomer. And I never let that go. Around 12 years old, I ground my first telescope mirror, and then, within a year or two, built a mount for it, and, and started off with a cardboard tube, and, and that went on and on. I kind of carried that passion for astronomy and building telescopes. So that's kind of funny thing. When I was deciding between high school and college, what I wanted to major in college, I didn't know if I wanted it to be astronomy or engineering, because I liked astronomy, but I liked building telescopes too. And I ended up deciding on engineering. I said, because when I built my first telescope, the very first thing I wanted to do with it was to build another one. Not so much to look through it. Like, I had so much fun building it, and it was like, oh, I knew I could do it better the next time. So I realized I'm more of an engineer. When you're that, when the goal after building the telescope is that you want to build another one and not that you want to look through it, that means you're really more of an engineer than a scientist, which is fine because that's what I chose. And so now I like doing outreach because, I don't know if you know, but astronomers are like drug pushers. It's like, hey, man, you got to check out what I'm seeing. You got to do what I'm doing. But the only difference is we don't make money doing it. But
I've got a 10-inch scope of my own, and I was the president of my local club, so I've got the bug as well. I love showing off the night sky.
Yeah.
So if somebody wanted to follow one of your pathways into engineering or into astronomy, how do you prep for that as a child? I mean, do you follow your passion? Is that enough? Just follow your passion?
No, it's not. So I have tips for people, for young people. One thing, the very first thing is join your local astronomy club. And if there's more than one, join them all. If there's one 20 miles in one way and 30 miles the other way, join them both. Hopefully those clubs are members of the Astronomical League, which is kind of like the world's astronomy club to join. And if it's not, then join the Astronomical League separately. And the Astronomical League has tremendous programs to get involved with, like variable star observing or multiple objects in the sky and recording data. This is science. When you start recording data and using your measurements to predict things or catalog things, that's science. And then beyond that, so now that's when you're really young. As you get older, see if you can get an internship somewhere. And don't worry about getting paid. I know that sounds weird, but it's so much more important that you intern somewhere. You'll figure out a way to eat and have money. And if you're young enough, your parents will maybe support you through this. But get an internship. It could either be at a national lab or a local university or NASA or Goddard Space Center or someplace. And then as an adult, You can get involved in things like the AAVSO, the Amateur Astronomer Variable Star Organization, where you can actually use your telescope. And then there's other, Minor Planet Center. You can record asteroids and minor planets and submit it. And this is what you can do into your adult life and be a useful part of the system. Because, astronomy is a funny endeavor. Amateurs contribute a lot to astronomy science. So it's not just to go out and look at the stars and have fun. You can actually, it's still fun, but you can, you can make contributions to the field.
All right, Steve, thank you so much for the explanation of your work, and those tips are excellent. Those are great tips for getting into astronomy and pursuing your passion. All right, well, I've got to run because I've got a meeting to go to. So thank you so much, Steve. Really, seriously appreciate that.
No, thanks for having me, Dave. This is awesome. I'm glad the EarthSky subscribers are going to get to see more about Vera Rubin, and there's more to come.
There is more to come, and we'll have you back and your colleagues when that happens.